All right, let's talk about absolute convergence, conditional convergence, and divergence. So a series can be classified as one of the following. First of all, a series is called absolutely convergent if the absolute value of the underlying series is also convergent. So this would be, for example, when you have an alternating series that would converge even without the alternator, then the series is absolutely convergent. If we call a series absolutely convergent, then we also just call it convergent. And then last, we call a series conditionally convergent if a series is convergent conditional on the fact that it has an alternator, meaning without the alternator, the underlying series would diverge. That means this series is conditionally convergent. So let's look at examples. Here we have an alternating series. We know from a prior page earlier in today's lesson that this alternating series converges because the underlying series is a sub n equals 1 over n squared. This series is has positive terms. It is decreasing as n goes to infinity, and the limit of the series as n approaches infinity is equal to 0. So by the alternating series test, this series converges. But the underlying series, 1 over n squared, is a convergent p series with p greater than 1, it's equal to 2, and therefore, since the underlying series also converges, this guy is called absolutely convergent because if we were to take the absolute value of this underlying series, we would get this underlying series which converges, which means that our alternating series absolutely converges. So let's look at another example. If we look at -1 to the n minus 1 over n, first of all, the terms of the underlying series are 1 over n. They are greater than 0. They are decreasing as n goes to infinity. And the limit as n goes to infinity of 1 over n is equal to 0. So the alternating series converges by the alternating series test. However, the underlying series, 1 over n, which you'd get by taking the absolute value of our series, you would get the series of 1 over n, is the divergent harmonic p series. So, since the underlying series is divergent, this series is only convergent conditional on having the alternator. Without the alternator, this series would diverge. Therefore, we call this guy conditionally convergent. And again, that means it's conditional on having the alternator. That should say conditionally convergent. And this one, of course, I didn't write down, but I'll write it down, is absolutely convergent. So let's look at two more here. This one is the 0.01 to the n is really 1 over 100th to the n. So this is my underlying series is 1 over 100 to the n. Well, here's the really cool thing, is that since I know that this is a geometric series with r equals 100, I know that the absolute value of r is less than 1, so this series converges. So that means that the absolute value of this series converges, and that means this series is absolutely convergent, and I don't even have to do the alternating series test. So if I can show that the underlying series converges, then the series flat out converges, and it absolutely converges. All right, example number 4. I'm just bringing this in here to remind you that cosine pi n is an alternator. So honestly, this is the exact same problem as number 1, in that there is an alternator times 1 over n squared. And so by the alternating series test, we know that this one will converge, but we also know that the absolute value of the series, 1 over n squared, is a convergent p series with p equal to 2, which is greater than 1. So this series also absolutely converges.